Hi everybody, today we are going to move into lesson 3.1 and we're going to be starting on page 25. You're definitely going to want a pencil and a highlighter handy. Now, one of the things we talk a lot about in this lesson is vocabulary and the idea of creating vocabulary words. So think about when you have a dictionary and you need to look up a word you don't know. And have you ever gotten to the point where you look up a word or something you don't know, and then the definition is just made up of more words you don't know? Well, eventually it has to come back to a set of words you do know if you keep looking these words up. And that's where the idea of the axiomatic system of geometry comes into play. Basically, what the axiomatic system of geometry is that we are basically going to have a starting point of terms that we know are true, and then the rest of our logic is built off of that system, and we can keep proving more and more things true and then using them to build logic. And the idea goes back to, again, if you read these definitions, the word fountain, normally if you think of a fountain, you're probably thinking of this thing right here, right? But the definition is a roundel that is very weighty of 6 argent and azure. You're probably like, what the heck? That doesn't make any sense. Unlike the word gage, which I didn't know what that was, but it says it's a belt that is worn over your right shoulder to support a shield. So this thing right here. Okay, that makes more sense because it's words I understand. And that's where we come back to this axiomatic system is we need to basically a basic set of definitions in which to build all other definitions. And that's where the idea of our undefined terms of geometry come into play. So these are our 3 undefined terms. And if you don't have them written down, I definitely would. It is point, line, and plane. Because basically what we're able to do is build from those 3 words all other vocab words. For instance, a ray is a line bounded by one endpoint and extending in one direction. So we're using point and line in our definition of ray. Or, for instance, collinear points. Well, collinear points are points that lie on the same line, right? So we can draw these in. Here's a lovely picture. These are all collinear points because they're on the same line. So again, if you want to write that point that lie on the same line. Those are collinear points. Well, coplanar points are going to probably be, you guessed it, pretty similar to collinear points, but this time they are on the same plane. So here's our plane. Here are our coplanar points on the same plane. So again, those are going to be points that lie on the same plane. And again, these definitions are using those undefined terms like points, plane, line. Those are all undefined terms. And now that they're defined, we can use them forward. Okay. Now, same thing here. These are just some more examples, but with angle, we can come up with the definition of angle because we have the definition of ray. All right, we can create the definition of angle is 2 rays with a common endpoint because we defined now on the last page what a ray is. And now that we defined angles, we can, use complementary angles to describe, angles that add up to be 90 degrees. So if this angle is 30 degrees and this angle is 60 degrees, well, when we add them together, they equal 90 degrees. But we first had to know what an angle was before we could know what a complementary angle is. So we start building and building and building these definitions and ultimately use them to define other things. Well, this is really similar to what you did back in algebra, right? So notice all of these different algebraic properties. Addition theory, subtraction theory, multiplication, distribution property. All of this allowed you to start solving because you knew those properties were true. So essentially, notice if we are given an equation, we can justify each step using those algebraic steps, right? For instance, this was given to us. This is the original proof, okay, the original setup. And you could do this a couple different ways, but maybe you say, okay, I'm going to add this to the other side. I'm going to have 4.5 x's on this left-hand side and none left on my right-hand side. Well, why was I allowed to do that? I used the addition property that is located right up here, right? The addition property, okay? And then you probably are thinking, if we're going to continue solving, okay, well, I need to move this 9 over to the other side, right? And I can do that by subtracting, oh my goodness, rid of that, this x here, and I can subtract that 9 over using the subtraction property. So now instead of 18, I have 9 on the right-hand side. Okay. And then last but not least, to get x by itself, I need to get rid of this 4.5 out front, and I'm going to undo that multiplication by doing division. So 9 divided by 4.5 is 2. Okay, and again, we were able to do that by division. What we just informally did was a 2-column proof. Okay. Now notice this is set up a little bit prettier in example A, but what we did was we took the given and we proved by the end that x equals 3 is the answer here. So for instance, there's a couple ways you can go about it, but the way they have it set up is it looks like the first thing they did is they added this 1 to the other side. So they made this, added the 1 over, so we now have 12, and they used the addition property. And then from there, they distributed through the x plus 2, the 3, by using the distributive property. Then they moved this 3x over here to create 2x using subtraction. Subtracted again to move the 12 over. 6 minus 12 is -6. That's a subtraction property. And then we used division to get x by itself. And then last but not least, these two flipped around by the symmetric property, right? Because whether we say -3 equals x or x equals -3, that is symmetric to one another, okay? So same idea now in these columns here. One thing you're going to notice is that we always start with given, all right? That is always the first thing in your proofs, right? Notice in each of these, it was given that that was our starting point. So same thing here. It is going to be given that this is our first step, right? They gave us that. And then from here, this is kind of a weird way to go about it, but it looks like what they did is they multiplied both sides by 10. Well, that's a property that you can multiply on both sides as long as you do it to both sides in the equation. So what they did was they used the multiplication property. Well, from there, it looks like they simplify. 10 divided by 2 is 5. 10 divided by 5 is 2. They just substituted in values that are the same as 10 divided by 2 and 10 divided by 5, which are 5 and 2. And then from here, it looks like that 5 got distributed and that 2 got distributed using our distributive property. And then moving right along, it looks like we moved from having this 2x over here, we subtracted it over using the subtraction property. Subtraction property. And then almost done here, looks like we got rid of this 15 and added it over so that the 12 became the 27 property. And then finally, last but not least, to get x by itself, we had to use the division property. Both sides by 3 equals 9. All right, now try letter B on your own. I'm going to create a two-column proof to prove, all right, what x equals. All right, now, finishing up the last couple of things here. Number 5, why is it important, all right, to have the undefined terms of the geometry? Well, it's important to have the undefined terms because it builds all the other vocabulary right from it. So again, we're building all of the other vocabulary words by being able to use our undefined terms. Okay, so again, that's number 5. Now, number 6 then is asking us what is the relationship between a conjecture, a theorem, and now our two-column proofs. Well, these are really important because what happens is you can use a two-column proof to prove a conjecture is true, right? These two-column proofs are going to be able to allow us to prove our conjectures are in fact true. Well, once the two-column proof proves our conjecture is true, then that conjecture is now a theorem. So that's kind of the connection between these. And we talked about that a little bit last lesson, that our two-column proofs allow us to have theorems created, making those conjectures proven true without a doubt. Right? Last but not least, number 7. Notice everything is good in this proof so far. We talked about the distributive property, wrote down the given, distributive property, addition by adding, subtraction by subtracting. But what happens here is then after step 4, they said they wanted us to multiply and get this final answer. Okay, this is not correct. We don't want to use multiplication here. What we instead need to use is, in fact, division, right? You want to divide this 9 so that you end up getting x to equal -1, not 81. Okay, so don't be fooled by bad proofs, right? Thanks, everybody.